As metals lose electrons to form cations and establish a noble gas configuration, meaning that octet arrangement, the electrons are lost from the valence shell first. For example, magnesium generally loses 2 electrons from its 3s subshell to look like neon. So you have magnesium going to magnesium 2+, so the electron configuration of magnesium is neon 3s2. What happens is it loses those 3s2 electrons and then becomes isoelectronic with neon. And has that noble gas configuration. Transition metals also lose electrons from the valence shell first, which is not the last subshell to fill according to the Aufbau sequence. For example, zinc generally loses 2 electrons from its 4s subshell to adopt a pseudo-noble gas configuration. So you have zinc, which is argon 4s2 3d10. It's going to lose its outer electrons first, the 4s2, because of that, losing those 2 electrons to get that positive 2 charge. And so it gets isoelectronic with argon, except that it has that 3d10 on it, and argon doesn't have that, and that's why we refer to this as the pseudo-noble gas configuration, because it has those extra d electrons attached to that noble gas configuration. When 2 nonmetals bond, they often share electrons since they have similar attractions for them. This sharing of valence electrons is called a covalent bond. These atoms will share sufficient numbers of electrons in order to achieve a noble gas electron configuration, being an octet or a duet. You can represent the formation of the covalent bond in H2 as follows. What happens here is they're both looking to get their full shell, which in this case will be a duet. So hydrogen will each make their electron available and share it to get electron shared between them. So in essence what happens is that both of them have their duet. This uses the Lewis symbol for the hydrogen atom and represents the covalent bond by a pair of dots. To complete the duet for hydrogen, each hydrogen atom shares their electrons between them so that they both have a duet. The shared electrons in the H2 spend part of the time in the region around each atom. In this sense, each atom in hydrogen, meaning H2, has a helium configuration, meaning it has its complete duet. Hydrogen happens to be found in nature as H2, not as H, because this arrangement of sharing electrons is more stable. The formation of a bond between hydrogen and chlorine to give HCl molecule can be represented in a similar way. You have hydrogen, which has 1 valence electron, and chlorine, which has 7 valence electrons, which basically the same thing happens. Hydrogen will offer to share that electron, and chlorine will offer to share their electron. And what we get is a duet around hydrogen. So we end up with our 2 electrons around hydrogen, and then chlorine now has an octet by sharing the electrons. Thus, by sharing electrons, hydrogen has 2 valence electrons about it, has a duet, and chlorine has 8 valence electrons around it, has an octet, isoelectronic with argon. Formulas such as these are referred to as Lewis electron dot formulas or Lewis structures. Electron pair is either a bonding pair shared between atoms or a lone pair, electron pair that is not shared. So these 2 electrons between the hydrogen and chlorine atom are called bonding pair. These other 6 electrons are called lone pairs because they're not bonded to anything. When bonds form between atoms that both donate an electron, you have a covalent bond. So when both species are bringing an electron into that bond, that shared pair, that's referred to as a covalent bond. It is, however, possible that both electrons are donated by one of the atoms. This occurs is called a coordinate covalent bond. So in this case, you can see that B is bringing both electrons to be shared between them. In the molecules described so far, each of the bonds has been a single bond, that is, a covalent bond in which a single pair of electrons is shared. It is possible to share more than one pair of electrons between atoms. Due to the lack of available electrons, atoms must share more than one pair of electrons to obtain an octet. A double bond involves the sharing of two pairs of electrons between atoms. In ethylene, C2H4, there are only 12 electrons available. For each hydrogen to have a duet and each carbon to have an octet, by using only 12 electrons, the two carbon atoms must share 4 electrons to make a double bond. Here's the Lewis structure of ethylene. You can see that we only used 12 electrons. 2, 4, 6, 8, 10, 12. That's all we have available based on valence electrons. Now, to share the 12 and still reach our octets and duets, we have to share more between the two carbons. So we have 4 electrons between the carbons. We couldn't give them just 8 by themselves if that would take more electrons than we have. Notice hydrogen has 2. Well, the hydrogen has 2, 2, and 2. So each of the hydrogens has their duets. One carbon has 2, 4, 6, 8. So it has an octet. The other carbon has 2, 4, 6, 8. It has its octet. So we only used the 12 electrons available, and we were able to give everything octets/duets. Now, what we tend to do is we don't write the dots. We tend to do for bonded pairs is write a single line when it's a single bonded pair. If it's a double pair being shared between two atoms, we write a double bond. Triple bonds are covalent bonds in which 3 pairs of electrons are shared between atoms. In acetylene, C2H2, there are only 10 electrons available from its valence electrons. For each hydrogen to have a duet and each carbon to have an octet, by using only 10 electrons, the 2 carbon atoms must share 6 electrons to make a triple bond. You can see in the structure here that each hydrogen has its duet, and inside this green circle you can see the carbon has 2, 4, 6, 8 around it, and the other carbon has 2, 4, 6, 8. And we only used a total of 2, 4, 6, 8, 10 electrons. Even though the duets and octets are met, only 10 electrons were used. 2 between the hydrogens and carbons, and 6 between the carbons. This is accomplished by the carbon atoms sharing 6 electrons. Writing this with our typical bond arrangement, we typically say a bonded pair is represented by a single line, 2 bonded pairs by a double line, and in this case we have 3 bonded pairs is by a triple bond. So we tend to write it with 3 lines between the 2 carbons. The length and strength of a bond between atoms varies with the amount of electron density present. That means the number of bonded pairs between 2 atoms. Single bonds are the longest and weakest bonds, while triple bonds are the shortest and strongest bonds. So bond length for a single bond is approximately 154 picometers for a carbon-carbon bond. Bond energy associated with that is 346 kilojoules per mole. While a triple bond length is smaller because electron density shrinks a little bit because you have 3 pairs of electrons there. You get 120 picometers. But the strength of that bond increases tremendously. It's 835 kilojoules per mole, where your double bond is in between in length and in between in energy. The bond order determined by the Lewis structure is the number of pairs of electrons in a bond. Bond length depends on bond order. As the bond order increases, the bond gets shorter and stronger. So a single bond has a bond order of 1, double bond 2, and a triple bond 3. Why does a multiple bond occur? There's not enough electrons available in the structure for each atom to have an octet by themselves. Therefore, they must share their electrons. Let's look at the molecule nitrogen, N2. There are only a total of 10 electrons available, 5 valence electrons coming from each nitrogen to complete octets. So you start off with, you have nitrogen with 5 valence electrons on each nitrogen. So they're going to share things. So you have nitrogens will share electrons. When you do that, the nitrogens can share each electron to form a bond between them. However, this arrangement will not give each nitrogen an octet. It only gives each of them a total of 1, 2, 3, 4, 5, 6 around this nitrogen, and 1, 2, 3, 4, 5, 6 around this nitrogen. So what's going to happen is they're going to have to share more electrons. Try a different arrangement. So we take 2 more electrons and share them. And we count our electrons. 1, 2, 3, 4, 5, 6, 7 around the nitrogen. And 1, 2, 3, 4, 5, 6, 7 around this nitrogen. They still do not have an octet around each of them, so we're going to have to do this again. Now we have 2, 4, 6, 8 around nitrogen, and 2, 4, 6, 8 around this nitrogen, so they both have octets. And it took us how many electrons to do that? 2, 4, 6, 8, 10. And so we're now 10 valence electrons that we have. So what we end up with is a triple bond between the nitrogens. A polar covalent bond is one in which the bonding electrons spend more time near one of the 2 atoms involved. Basically, the atoms do not share the electrons equally. When the atoms are alike, as in hydrogen-hydrogen bond of H2, the bonding electrons are shared equally and a non-polar covalent bond results. Okay, it's the same atom, so they're not going to share it differently. They've shared exactly the same. When the 2 atoms are different elements, their electronegativities may differ enough to cause the bonding electrons not to be shared equally, resulting in what we refer to as a polar bond. Example, HCl. Chlorine has a higher electronegativity, so it gets a greater share of electrons, so they're not sharing electrons between them in an equal fashion. For example, the bond between carbon and oxygen in CO2 is considered polar because the shared electrons spend more time orbiting around oxygen atoms. Oxygen is the more electronegative atom. We say that the bond is polarized toward the more electronegative atom and that the bond is polar covalent. Since the electrons are not equally shared between the atoms, there's a partial negative charge on the oxygen since electrons are spending more time around the oxygen, and we denote that with a delta minus. And a partial positive charge on the carbon. It has less electrons are spending less time around it, so it has a depletion of electrons, so it has a slight positive charge. So we denote that with delta minuses on the oxygen and a delta plus on the carbon. The product of the magnitude of the charge on an atom and the bond length between the atoms is called the dipole moment. By definition, molecules are electrically neutral. However, many a molecule has a region of pole bearing a net partial positive charge and the opposite region of pole bearing a net positive negative charge, as in an example of this CO2. We have the oxygens have a slight negative charge and the carbon has a slight positive charge. As long as the charges do not cancel out each other, such a molecule has a dipole moment, which is equal to the vector sum of the dipole moments of all bonds in the molecule. Such molecules are said to be polar because they possess a permanent dipole moment. So we have a dipole moment between the oxygen and carbons on each side. However, if they cancel each other out, then we have no net dipole, okay, and the molecule is nonpolar. If they do not cancel out each other, then we have a net dipole and we have a polar molecule. The dipole moment of a molecule, being a vector, has a direction, which is shown using the following symbol. The arrowhead of the symbol is pointed toward the negative end, and the plus sign toward the positive end. So we tend to put the positive end around the delta plus and the arrow pointing toward the negative end. Here's an example, HCl. Hydrogen has a delta plus, chlorine has a delta minus, so we write the positive end over the hydrogen and point the arrow toward the chlorine. This is a polar bond because they're not the same atom here and they're not sharing them equally due to electronegativity difference. There is a net dipole moment because it's not canceling out, it's only pointing in one direction. I don't have a vector pointing in the other way. So this whole molecule is polar. So HCl is a very polar molecule. Molecule may not have a dipole moment despite containing polar bonds that do. For example, each of the two carbon-oxygen bonds in CO2 has a dipole moment, but the CO2 molecule has no dipole moment because the dipole moments of the two carbon-oxygen bonds are identical in magnitude and opposite in direction, resulting in a vector sum of 0. Thus, the molecules that are perfectly symmetric have a 0 dipole moment. These molecules are considered nonpolar. So going back to our CO2 example, we had our negative charges and our positive. We can write a vector of a plus pointing out toward the oxygen in one direction and a vector pointing out in the other, where we have dipole moments on those bonds, but if you sum up those dipoles, since they're in opposite directions, they cancel out each other, so it's a net 0. So although we have polar bonds, the CO bond and the CO bond are both polar bonds, there is no net dipole moment. We have opposite dipoles canceling out each other. Therefore, the whole molecule of CO2 is a nonpolar molecule. Molecules that exhibit any asymmetry in the arrangement of electron pairs would have a non-zero dipole moment. The ammonia molecule below is considered polar because the sum of the dipole moments do not cancel out. In fact, in this particular molecule, all dipoles are in the same direction and are additive. Therefore, ammonia is a very polar molecule. Here's the Lewis dot structure of ammonia, and we know that nitrogen is more electronegative than hydrogen, so we have excess positive charges on the hydrogen and a negative charge on the nitrogen. So our dipole vectors will be pointed as such, where we have the positive end pointing toward each one of the nitrogens, and a lone pair is extremely more negative charge than any atom, so therefore that's pointing out as well. So you can see that all four vectors are pointing up and are completely additive, so this is a very polar molecule. What we have here is a 3D picture of the ammonia. Notice that the shape of this molecule is in the form of a pyramid. We'll talk more about that when we get to the next section. How you determine the electronegativity of an atom to decide if and in what direction a dipole moment exists. Well, electronegativity is a measure of the ability of an atom and a molecule to draw binding electrons to itself. In general, electronegativity increases from the lower left corner to the upper right corner of the periodic table, with fluorine being the highest value. The current electronegativity scale, developed by Linus Pauling, assigns a value of 4.0 to fluorine and a value of 0.7 to francium. Metals tend to have values less than 1.9, while nonmetals tend to have values greater than 2.1. Here's a periodic table for all the different electronegativities. Notice that the general trend is that it increases to the right and increases up the periodic table. So generally you can look at the periodic table and make predictions of electronegativities, comparison between one species and another by knowing this general trend. Electronegativity differences between atoms that are greater than 1.8 are considered ionic bonds. This generally occurs with your metal-nonmetal bonds. This is why we make that generality and we say a metal and a nonmetal is an ionic bond, because based on these numbers, that's the general trend. Electronegativity difference between atoms that are greater than 0.5 but less than 1.8 are considered polar covalent bonds. Generally, this occurs with your non-metal bonds. So if the electronegativity between 0.5 and 1.8 occurs, then we're going to call that a polar covalent bond. Now don't get concerned about having to memorize this table. I'll tell you a generality that you can do to make your decision whether it's going to be a polar bond or not on the next slide. Electronegativity differences between atoms that are larger than 0 but are less than 0.5 are considered covalent bonds, but are essentially non-polar in nature. They're not going to share their electrons unevenly because the electronegativity is not great enough. Metallic bonding involves bonding between metal atoms in a solid and is also considered a covalent bond. One thing I want to bring to your note is where the location of hydrogen is on this table. Notice that hydrogen is a 2.1 electronegativity, boron's a 2.0, and carbon's a 2.5. So hydrogen falls right between boron and carbon on this periodic table. So when you're noticing your trends of electronegativities, you got to realize where hydrogen fits on that periodic table. The absolute value of the difference in electronegativity of two bonded atoms gives a rough measure of the polarity of the bond. When this difference is small, less than 0.5, the bond is nonpolar. Example, hydrogen and carbon. Electronegativity difference, you have a 2.5 minus 2.1 is 0.4, which is less than 0.5. Basically, the electrons are shared similarly between these atoms. Not one atom is getting a greater share than the other one. When this difference is large, greater than 0.5 but less than 1.8, the bond is considered polar. Example, HCl, electronegativity difference, 3 is 0.0 for chlorine, 2.1 for hydrogen, and is 0.9. That's greater than 0.5, less than 1.8, so this is considered a polar bond. The electrons are not shared equally and spend more time with one atom over the other, in this case being chlorine. Chlorine's more electronegative, so it's getting a greater share of those electrons. If the difference exceeds approximately 1.8, sharing electrons is no longer possible and the bond becomes ionic. Ionic bond is the ultimate in polarity. One species gets all the electrons. There's no sharing electrons. Basically, you transfer the electrons to the other species, and the formation of charged species occurs. This is our generality we go with. A metal-non-metal tends to be ionic bond. It's going to tend to be, for the most part, greater than 1.8. Now here's your generality for the other situations of your nonpolar and polar bonds for your covalent bonds. Generally, nitrogen, oxygen, fluorine, chlorine, and bromine. You take these 5 and you attach that to any other nonmetal, okay, another nonmetal, excluding these themselves, okay, what you have is a polar bond. Their electronegativity will be between 0.5 and 1.8. So generally, nitrogen, oxygen, fluorine, chlorine, and bromine attached to some other nonmetal will be a polar bond. Other nonmetal combinations will be nonpolar. Okay, they'll be less than 0.5. Homework 65.